In the last lecture, we had introduced you to the concept of measurement. We talked first about general measurement theory, and then we said that a special case of measurement operators are the projection operators. So this is called projection measurement or von Neumann measurement. And today we will do two things. First thing is to talk about what happens if your state is mixed state. How do you extend? What is the corresponding measurement postulate? So if you recall that we had defined our density matrix rho by sum over I Pi, that's the classical probability with which the state psi I is there in the mixture. So rho is sum over I Pi psi I, and let us suppose I am still talking about expressing the state psi I in a basis, and let us say that psi I is written as sum over j Cij Ej, where my Ej's are the basis states. Then by Born rule, my Cij, the coefficients, they are given by the product of Ej with the state psi I. Suppose I am observing the state psi I, and the probability of finding the state psi I in the basis Ej is then given by simply absolute square of this quantity. So what we now want to do is to see how this translates into the corresponding expression for the density matrix. Now this is a fairly straightforward thing, as you can observe from here, from the slide. Sum over I Pi Ej psi j absolute square. So you notice that if this is what we are observing, the state psi. So the question that I am trying to answer here is, I know what is the probability that the state psi I will appear in the basis state Ej. But since my total state psi is sum over I Pi psi I, supposing I am looking at this mixed state, then the probability of an arbitrary member of this assembly in the basis state Ej is then given by first the probability of picking up psi I, which is Pi, and then the probability that a measurement of psi I gives me the state Ej, so which is Ej psi I absolute square. And if I sum over that over all states I, then I get the probability that we observe the state psi in the basis state Ej. Now this absolute square you can simply rewrite as Ej psi I Ej, and since these are numbers basically, I rearrange them a little bit by writing this Ej sum over I, this sum I bring it inside, sum over I Pi psi I ket psi I bra, okay, and then Ej again. But this is my definition of rho. So therefore, the probability to observe the state psi in the basis state Ej is simply given by the matrix element of the density matrix in the basis state Ej, Ej rho psi Ej. Now, so the question is this, that suppose I have made a general measurement, then we have seen what we want to find out, what is the probability of the outcome. Now according to the quantum postulate, it is given by trace of dagger rho, I will tell you how, and after the measurement the density matrix becomes rho dagger divided by this probability of the outcome. So this is regarding density matrix. Remember, there is no square root in the denominator of that, because we are talking now about a density matrix which is a product of a ket with a sign. So in this case, let us look at what is this trace of dagger rho. So this quantity is, let us just rewrite it, trace of dagger let me write rho in its full form, that is pi psi I ket psi I bra. So I rewrite this as sum over I pi, and then it's a trace of dagger psi I. Now remember, the trace of a, we had talked about it earlier, the trace of a ket with a bra. So this is a ket, an operator acting on psi I. The trace of ket with a bra is simply the scalar product of the bra with the ket. So therefore, this is equal to sum over I pi trace of. So this trace evaluates to psi I dagger acting on psi I again. Now this is the what the trace stands for, and the after measurement, then the state becomes, go to the slide, the after measurement the state becomes rho dagger by trace of dagger rho. This is, this is a part of the postulate. It takes a bit of an algebra to prove this is identical to the case where we take the definition of rho in terms of sum over I pi psi I, and then we know what the postulate for the state is. So let me give you an example of how this works. Now suppose I start with the same example as before, that is, I take a 1 qubit state psi which is equal to alpha 0 plus beta 1. And let us suppose we are measuring the z component of the spin, so that my corresponding operator is sigma z. So sigma z operator, if you recall, is 0 0 minus 1 1. This is nothing but this spectral decomposition, because I know sigma z has eigenvalue either plus 1 or a minus 1. So this is the state corresponding to plus 1. This is the operator corresponding to the eigenvalue equal to minus 1. So therefore, my m0, which corresponds to the eigenvalue plus 1, is simply 0 0. What is my rho? My rho is psi psi So this is equal to alpha 0 plus beta 1, and the ket will, the corresponding bra is alpha star 0 plus beta star 1. Now you can easily calculate now by the previous formula that I gave you, what is trace of m0 dagger, m0, I have written down already m0 there, times rho. A trivial algebra will tell you this is equal to modulus of alpha square. We can see how. So this is trace of, let me just do this algebra a little bit. So this is m0 dagger, so I have got 0 0, again m0, so that 0 0 again. Rho is what I have written down here in this form. So let me just rewrite it alpha 0 plus beta 1 into alpha star 0 plus beta star 1. There is a error there. So let us look at this. This is equal to 1. Now again, so I have got here alpha 0, alpha star, etc. So I get this as trace of 0. Now this 0 0 is 1. This 0 1 is 0. So therefore I am left with a alpha from here. And then on the bra side I have got alpha star 0 plus beta star 1. Now since I am taking a trace, so I have got a ket and the bra, I know taking a trace means multiplying the corresponding bra with the ket. So this is equal to, simply alpha modulo square alpha star alpha times 0 0, which is equal to of course modulus of alpha square. So as a result, according to this, my post measurement state will be m0 rho m0 dagger divided by trace of m0 dagger m0 rho, and that is equal to 0 0. Then I have got alpha square divided by alpha square, which is nothing but 0 0. This is the corresponding density matrix. Another interesting thing that comes out is what happens if you repeat a measurement. Now, as I told you earlier, that since on making a measurement, the state collapses to a particular state. Supposing I am doing it in a basis and the state collapses to 0. Now if I repeat the measurement, the state of course would remain in that same state. But let us do the following. Supposing I have a system, we could start with that same alpha 0 plus beta 1. But this time I consider measuring in either the 0 1 basis, which is the computational basis, or in the diagonal basis. So if you now work out what is the result that I get if I make a measurement first in the computational basis and then in the diagonal basis. And in the second case, what I do is first make the measurement in the diagonal basis and then make the measurement in the computational basis. Now you can immediately see that the results are not the same. So I am doing a repetition, but what I am doing is I am changing the order in which the basis chosen is applied. First computational, then diagonal, or first diagonal, then computational. So let me come back to my same old state, psi equal to alpha 0 plus beta 1. So if I come to that, I am not going to repeat the calculation that I made earlier. Supposing I first measure in 0 1 basis. I know that I will get the state 0 with probability mod alpha square. And after I have got this result, my state has become 0. Now the question is this, that what do I get? Suppose I now make a measurement in the diagonal basis. So next measurement in diagonal basis. Remember the state 0 to which my system has collapsed after making my first measurement can be written as plus plus minus divided by root 2. So if I now make a measurement in the diagonal basis, it would give me plus with a probability half and minus with a probability half. So therefore, the probability of getting 0 plus as my result is given by alpha square by 2, and 0 minus similarly is also alpha square by 2. Now suppose instead I decided to first measure in diagonal basis. Now recall, what do? My state is still psi equal to alpha 0 plus beta 1. As I had said earlier, you have to first express it in the diagonal basis. That gives you alpha plus beta by root 2 plus alpha minus beta by root 2 minus. Since my first measurement is in the diagonal basis, the probability of getting plus is given by modulus of alpha plus beta absolute square by 2. So at that stage, suppose I have got a plus and I now measure the state in the computational basis. So if I measure the state in the computational basis, now my state had collapsed to the state plus. So therefore, I will re-express the state plus in terms of 0 and 1 and find out what result do I get. Now obviously, this probability is not the same as the probability for getting 0 plus. So plus 0 probability is not the same as the 0 plus probability. So far we have been talking about projective or von Neumann measurement. There is another special type of measurement known as POVM, which is a short form for positive operator valued measure. We need not go into the nomenclature, but this is non-projective. I mean, projective operators are special cases of this, but these are non-projective. The projective operators, projective measurements commute, POVMs need not. The other thing about the projectors were, they were orthogonal projectors in the sense PM prime was equal to PM times delta MM prime. There is the prime is at the wrong place in the slide, but POVMs are not necessarily shown. The other thing is, if I look at a d-dimensional space, there are exactly d number of projectors. In POVMs, this could be more than d. So POVM that I am talking about is a very special class of non-projective measurement and is a general measurement. So let me define POVM. A POVM is basically a collection of positive operators. You might recall that the definition of projective operators is an operator A is a positive operator if psi A psi is greater than or equal to 0 for every psi. But we will not go into this aspect of it. So first thing we say, we talk about a collection of positive operators. And of course I need completeness, so sum over I, EI is equal to identity. Now since this is a positive operator, we are in finite dimensional space, you can show it that this also happens to be Hermitian, and I can find out a representation of EI as equal to MI dagger M, MI. My postulates then tell me the probability of an outcome I is given by psi ei psi, or if you want to talk in the language of density matrix, this is simply equal to trace of rho ei. The post measurement state of the system is rho going to some rho prime, which is equal to mi rho mi dagger divided by trace of the same thing, which is the probability rho with ei. Now this is what the result will be after a measurement has been made, and if we read that state which has come. But supposing we do not read it, then it remains in the linear combination states, that is rho remains as sum over I mi rho mi dagger if not read. Remember, the reading is important because what the reading does is to collapse it into one of the possibilities. So therefore, this is what would happen if you don't read. If you don't read, all the possibilities exist. If you read, one particular state comes out. So that was what POVMs are all about. I will give you a couple of examples. The first one is fairly straightforward. Actually, this is also projection operators. But suppose I define instead E1 equal to not 0, 0, but as half of 0, 0, and E2 equal to half of 1, 1. Now, since I want completeness, I define E3 equal to identity minus E1 minus E2. You can prove that this is positive operators, and the completeness is by definition of E3 actually. So this is an example of POVM. Now, a very interesting example I will pick up from Nielsen and Chuang. The exact construction method is not important, but it will also see that POVMs are useful in trying to distinguish non-orthogonal states. The point that I want to make is, suppose, okay, we will come to that question, but supposing I define E1 as equal to square root of 2 divided by square root of 2 plus 1, 1, 1. E2 is square root of 2 by square root of 2 plus 1. These, you can check that these are required for both normalization and for making them complete. So this is 0 minus 1 ket multiplied by 0 minus 1 bra. And E3, in order to ensure completeness, is simply equal to identity minus E1 minus E2. So these are my 3 elements of POVM. Of course, the moment you see this definition, you can immediately conclude that these are not orthogonal projectors because I am in 2-dimensional space, but I have 3 elements. Now, the interesting thing about this POVM is that suppose I am given 2 states. One is a psi 1, which is simply the state 0. The other one is a state psi 2, which is the state 0 plus 1 by root 2. Now, you cannot distinguish these states by a orthogonal projective measurements. The reason is that 0 plus 1 by root 2 has a projection both along the state 0 and along the state 1. But let us look at what does this POVM that I have written down does. Now look at it. Supposing I get one state which I don't know which one, whether it is psi 1 or psi 2, and I get the result E1. Now if I get the result E1, the state could not have been psi 1 because it is orthogonal to that. Now since I have only two possibilities, psi 1 and psi 2, if I get the result E1, the state must have been psi 2. On the other hand, if my measurement gives me the result E2, you notice that this is orthogonal to this operator acting on psi 2 gives me 0. So therefore, the given state could not have been psi 2, and since the only option is psi 1, it must have been psi 1. So I distinguish between psi 1 and psi 2 definitely in case where my measurement is E1 or E2. Now what happens when my measurement is E3? In that case, no conclusion can be made. The conclusion thereof is that using P of A, I am able to distinguish the two states. Not always, because if I get a result E3, I don't know what that state was. But when I do distinguish them, I never make a mistake. In other words, if I get E1, I know the state is psi 2. If I get E2, I know the state is psi 1. So whenever I am able to distinguish, I distinguish definitively. Occasionally, I can't come to a conclusion. So this is the positive operator valued measure, which is non-projective measurement, and we have seen it has some interesting aspects to it.